All right, Nathan, if you'll check your YouTube, see that we've got me going live. Testing. All right. No, I know. I'm wanting the stream to be checked. Okay. Well, they're working on that. When last we left off, before I got so sick I couldn't think straight, we had talked about converting, well, what a logarithm was, and converting between logarithmic form and exponential form, because they basically undo each other. They're the same way that a square root undoes a square power. We talked about how to go from the logarithmic equation to the exponential form. Any questions on this, or do you want to see one more quick example before we slide on? Okay, so I take silence as you don't want to see an example. And then we also had regular exponential equations going to logarithmic form. Does anyone want to see an example of this one before we move on?
Can we just do 10 just in case?
Number 10, just in case. All right. So remember that our recipe is base to some exponent equals some number gets converted to the logarithm of some base of some number equals the exponent. So base is there. Exponent. And then what the value equals. All right, looking at what I was given, this is the base. Here's the exponent on that base, and here's the value that it represents. So log the base of the number equals the exponent. And this gets read as the log base 36 of 6 equals 1/2. Questions? Hi, guys. The microphone's starting to pick you guys up. Do y'all have any questions for me on this? Okay, because there was conversation amongst you guys, and that was okay. I was just hoping that I could answer something for you. And then we had something called the common base. So when you have a base 10, it's called the common log, and it gets written without the number. How did we feel about evaluating some of these logarithms? Are we okay with evaluating the logarithms? Thumbs up. Okay, cool. Using the change of base formula. The trick is just trying to find a base that feels happy with both of them and doing as much as you can. All right. Then we started on the log properties, the product property. Now these properties should feel very much like the exponential properties, wherein with the exponentials, if you were multiplying things of the same base, you would add the exponents. And so here, when you have the logarithms of two things being multiplied together, you can break it up into two different logarithms being added together. Here's the quotient property. And the power property. There's some examples that we've done on these. Does anyone want to see me do another example just as a refresher? Hold it right here. Okay. You want me to zoom in? What am I zooming in on, Nate? Did anyone else walk in when? Okay, cool. All right, so now that you're done copying things, did anyone want to see any of these worked out? Just that refresher. 17? 18. Which one? Or yes. 18? All right. So looking at number 18, my first instinct is to freak out because, oh my God, there's a square root. And then the next thing that I want to do is I recall that I can change out square roots for fractional powers. So that's going to be the change I'm going to make. This is the log base 7 of w raised to the 1/2 power. Do you need the reminder on how we go from square root to fractional exponents? Yes? Okay, so our rule for going from radical stuff is, remember, this is a two-way street. We can go in either direction. Oops. Did you see the recipe there, Caitlin? All right, feels okay? Yeah. So now that I've got, hi guys. Thank you. Now that I have this without the square root, I have it with fractional powers. I'm going to use the power property of logarithms, which says, I'll wait. Bye. I'm in the middle of a lesson. Now that I have this written with exponents rather than in radical form, I can use the power property of logarithms to grab this exponent here at the top and shove it down as a multiplication in the front of the logarithm. That is what this property lets me do. And now it's as simplified as I think I can get it. Yeah. That's it. That's all there is to this one. Questions, comments, concerns? All righty. The putting it all together has you rewriting as single logarithms and then expanding the logarithm as much as you can and writing it in multiple logarithms. So this is just you playing with those log properties over and over and over again, and all mixed up all in one problem. Okay? So I'll leave that there for you. Shall we talk graphing? Hi. Shall we talk graphing real quick? Yep. All right. The logarithmic parent function is f of x equals the log of some base x. The variable's inside the logarithm. And the base is what changes. Now, the logarithmic function is the inverse of the exponential function, provided that the bases match. If you look at this example that's here for us to sketch, we notice that this logarithm doesn't have a base listed. What did we say that we assume if we don't see a base listed on our logarithm? Yeah, it's 10. Yep. So if we don't see a base listed on the log, it's assumed to be a base 10. Our exponential here is base 10. Let's sketch both of these. Y'all can go to your favorite Desmos.com to take a look at these. And that's what I'm going to do. I'm going to collapse this down and I'm going to go to Desmos. Desmos. Graphing calculator. All right, and we want logarithm. Let's see, functions, list operations, distributions, calculus, log. All right, so there's the log base 10 of x. And then I'm going to do 10 raised to the x power. And there they are. That's what they look like. Remember that exponents are inverses of each other. Always seem to reflect over this line y equals x, that diagonal line that runs along the, I wish I could draw on this particular thing. Oh, you know what? I can. How do I screenshot again? Like this. I did it. I did it. Look at me go. I'm so proud of myself. Thank you. Okay, now I don't know how to use the ruler. Oh, there it is. Look at me. I'm learning all this stuff with my iPad. Oh, I'm so proud of me too. Okay, but this would be the line of reflection. Okay, I missed a little bit, but that's close enough. Okay, the red one is the logarithm. The blue one is the exponential. There it is. They're reflections of each other. I'm so proud of myself I could do that. All right, so let's sketch these. I have the sketch here at the low bottom of my thing. So logarithms look like it goes like this. And this is 1. And then the exponential goes like this. And this is 1. There they are. Did y'all sketch them? All right. Because we can only graph base 10 logs, some calculators. Hi, guys. There's some side conversation later, please. There's enough distraction for me today. Because most graphing calculators can only do base 10 on the logs, you're going to have to use the inverse exponential function and then invert the tables in order to find the table for your log function, which means I got to turn this into its exponential form. All right, so reminder, here's how we turn this into exponential form. The base is 2. This is the exponent, and this is the number that the exponent is equal to. So we have x equals 2 to the y. Flip those to get the inverse, and this is the exponential function that we want to graph, or we want to get the values of in order to flop them to graph it. So I'm going to grab some coordinates, some values for this exponential function that is the inverse of that log function up there. So this is now 2 to the 0 or 1. This is 2 to the 1. This is 2 to the 2. This is 2 to the 3. And then if I'm going to grab the inverse to turn it into log base 2 of x, which was my original equation, I'm going to flop them. And all I'm doing is exchanging the values. Sorry about writing 5 here. I don't know what I was thinking. And this is what I want to graph. There's some rainbow ones there, but I'm not in there. All right, I'm gonna graph them. When x is 1, log is 0. When x is 2, it's 1. When x is 4, 2, 3, 4, we've up here at 2. And when it's 3, it's at 8. Or when it's 8, it's at 3. 4, 5, 6, 7, 8. 1, 2, 3. All right, there's my log graph. What's the domain?
X is greater than 0.
X is greater than 0. Will it ever be equal to 0?
No.
Ooh, it's an asymptote. Okay, so I have an asymptote at x equals 0?
X is greater than 0.
Beautiful. What's the range?
Y is infinity.
All of them.
Yeah, all numbers.
All real numbers.
To infinity and beyond.
Yes, to infinity and beyond. As x is approaching infinity, positive infinity, what value is f of x approaching? Woohoo! And as f of x is approaching negative infinity, what value is x approaching? Yeah. Is there an x-intercept? Where is it?
1,
Can you give me the coordinates, please?
1, 0.
1, 0. 1, 0. Because you always call the x direction first. 1, 0. Good job. All right, I'll let you practice that. The graphs get a little more wonky, but it's because they start doing transformations on you. But remember, you want to go through that inverse to help you out, okay? So create the inverse, and then, whoopsie, and then you can go from there. All right, what was the next thing? Oh, let's solve them. All right, to solve. Sorry to whoever was trying to teach this and wrote on my thing. I'm going to erase so that I have a clean slate to work with. It's not that I don't love you. We're going to condense the logarithm. Then we're going to use the one-to-one property that says, hey, if I have 2 logarithms on either side of an equal sign that have the same base as each other, then the stuff I'm taking the log of has to be equal to each other. This is the same sort of idea when we were trying to solve exponentials. When I had exponentials with the same base, I could throw away the bases and look at just the exponents. Hi. Thank you. It's the same idea. All right, so let's do number 1. Are they the same bases, yes or no?
Yes.
Yes, which means I can ignore the log and the base and grab just the stuff I'm taking the logarithms of. And then solve it from there. I'm happy to set up one more. If there's any others on this page that look, oh my God, what did I do? iPad. Are there any other logarithms on this page that look particularly challenging that you would like to see done?
Let's do number 7.
Number 7. Oh, that one does look ugly. All right, I'm going to have to apply my laws and properties of logarithms. As I'm looking at this, I notice that there's really only 2 logarithms in here. I have this logarithm and this logarithm. So really, all I have to do is find a way to get this coefficient into the logarithm and we'll be fine. That's our power property at play. Our power property allowed us to take an exponent that was hidden inside of a logarithm and pull it down as the coefficient, the number in front of the logarithm, which means I can go backwards. I can take a coefficient, a number in front of the logarithm, and pull it up as the exponent of the thing I'm taking the log of. Now, for a notation standpoint, this does have this kind of invisible parentheses on it. And so that's why we're affecting the thing inside the logarithm. Sorry, I typoed. That's supposed to be a 6, not a 2. And now that the logs with the same base are there, and there's only one log on each side of the equal sign, I can throw those away and work with just the stuff I'm taking the logarithm of. And this is a fairly straightforward equation to solve. Wait, are you panicking because, oh my God, there's a fractional exponent?
It's 5.
How did you get 5? Because that 1/2 exponent means that it's a square root, but it's not just 5, it's plus or minus 5. This thing has 2 possible solutions. All right, from here, I feel really confident that you can get it. Sorry, I'll leave it zoomed in for those of you who like to take pictures. Okay, are there any others in this section that look particularly complicated that you would like me to work on? Or at least get you started. Number 6. Number 6 does look complicated because number 6 has 1, 2, 3 different logarithms. One of the sides has 2 logarithms. We have to mush those 2 logarithms into one. We have to condense it. I notice the operation between them is a subtraction, which tells me I need to use my quotient property of logarithms. The quotient property of logarithm says that if I had the logarithm of something that was being divided, some sort of fraction, I could rewrite it as 2 separate logarithms with numerator being subtracted, having subtracted from it the denominator. So this becomes my numerator, and this becomes my denominator. And so I can combine that into the single log base 4 of 68 over 4 equals log base 4 of 3n plus 11. And then from here, the rest of the steps apply in that I only have one logarithm on each side. Check. Are they the same base? Check. Which means my equation is the stuff without the logarithms. Huh? The logs don't cancel each other out. It's like if I had, say, something like this. 2 to some variable equals 2 to the third. Well, obviously the x has to, like the exponents have to be equal. Otherwise, those things aren't equal. Well, the same idea here. If the logarithms are equal, then the stuff you're taking the logarithm of have to be equal to each other. That's that one for oneness. We had some good questions happening today.
Isn't it like, if like log 4 was the exponent of number 4?
Yeah, okay. So Caitlin, you had asked something about the logs canceling out. And Ricardo reminded me, thank you very much. If I had the logarithm of some base, and I had here something that was carrying an exponent that matched that base, then the logarithm in that exponent would essentially cancel out. Right?
No, the log 4 was the exponent and 4 was the base.
Yeah. Yeah, I think that's right. I don't want to get into the weeds about it because that's not the point of this one, but I think you're in the right spot. Okay. And now we can use this to solve equations. So we've learned all these tricks and now we're going to actually do stuff with it. Hi guys, you with me? Okay. So again, oh, this is the same one? Oh, I duplicated that page. I'm so sorry. All right. If you have a logarithm and you don't have logs on both sides, you have log equals a number. You're going to condense and isolate the logarithm. So make sure there's only one logarithm in the entire equation. Then shove everything else to the other side of that equation, and then swap it to an exponential and solve the exponential. I'm going to do number 12 for you guys. So I see a logarithm. It's right here, and here's the stuff that it's being taken the logarithm of. Those parentheses then tell me where that logarithm starts and stops. It stops after the 8. So I want to get this 7 off to the other side. I'm going to add it to both sides. And now I can swap it to exponential form. Remember that exponential form does this. I always get them backwards, but okay. Where we have the base and then the number being raised to that base, or that number raising the base. Okay. I cannot talk anymore. Okay, so we're going to swap that out for the base being raised to a power equals the stuff I was taking the logarithm of. There we go. Okay, so the base is 3, the exponent is 4, and the stuff I was taking the logarithm of is 4x plus 8. And then I would solve that standard equation. Nothing too complicated. The numbers just get a little big with those exponents. Do you want to see another one set up, at least to this point? Of course. Don't ask. Just take. You can even clip it if you want. Not lick, clip. Wow. Okay, did you want to see another one set up? Okay, which one? 13, 14, 15, or 16? 16? Yes, please, 16. Okay. So looking at this item, there are 2 different logarithms, one here and one here. So I just need to condense them down into one logarithm. To do that, I'm going to consider the operation that lives between them. This is addition, which triggers the product property of logarithms. That says originally, when I had the logarithm of stuff being multiplied together, I could rewrite it as 2 logarithms being added. Well, I could do it the opposite direction. I have 2 logarithms being added, which means I can rewrite it as a single logarithm composed of these 2 things being multiplied together. And in this case, I use those square brackets just so that way I wouldn't have a bunch of round parentheses sitting next to each other, which would confuse my brain. And now I'm going to do my swappy swap. There's the base. There's the exponent. There's what it equals. Base, exponent, stuff it equals. There's no base. on this logarithm? Corey, help. There's no base on this logarithm. What number do I assume it is?
10.
10. It's the number of fingers you have.
Okay, I remember it like that.
And then this becomes a standard quadratic equation for you to solve. Which means you can go to factoring, you can go to completing the square, you can go to quadratic formula. I don't recommend synthetic division or long division. All right. We're closing up. We're going to solve some exponential equations. Method number 2. Hi, guys. We're going to use logarithms to solve this. So we're going to isolate the thing that has the variable in the exponent. So we're going to get it all by itself. Then we're going to take the log of both sides to turn it into a logarithm. And we may need to expand the logarithm in order to solve that log equation that we're creating. Rounded answers may not produce exact same answers, but they're going to be very close. So when you're putting this back in to check for your extraneous solutions, which hint, you need to be doing that for all of these. I haven't been doing that step. You'll just want to make sure that you're getting close, okay? 3 to 4 decimal points of precision should be enough.
Miss, you should drink your water right now. Preservation. Yay. You sound like you need it.
Yes, I did. Thank you.
You're welcome.
Okay. Let's start with number 5. All right, looking at number 5, here's the thing that is carrying the variable, the exponential. Is the exponential alone, or does it have stuff that's happening to it? I highlighted the thing that is the exponential, the thing that has the variable in the exponent. Is it alone, or is there stuff happening to it? Okay, what's happening to it? Be multiplied by 4. How do I undo multiply by 4? Divide by? Beautiful. So doing that to both sides, I get 7n equals whatever that is.
Like, 30.
7, which you can't see. My calculator's not bright enough. Oh, that did not help at all. 37. And then I'm going to take the log of both sides. This is the base. This is the exponent. This is the stuff I'd be taking the log of. So it's going to be the log of the base, the stuff I'm taking the logarithm of, equals the exponent. Log base 7 of 37 equals n. That's not a pretty nice logarithm. That base is not, yeah, in 37. So I'd use the change of base formula, but those are both prime numbers, which means I'm not going to find a nice base, but I can find something that my calculator can deal with, and my calculator does base 10 very, very well. So n equals log base 10 of 37 divided log base 10 of 7. And when I throw that in my calculator, let's see if I can get it to work here. I'm trying to get it to work for YouTube, but it's like, it's putting a weird glare and spotlight. It's just not happy. Okay, so in my calculator, I am pushing the log button as soon as I can find it. There it is. And I'm going to type 37, and I'm going to close the parentheses. I'm going to hit divide, and then I'm going to press log again, and then type 7, close that parentheses. And when it's done, it gives me that n is approximately 8.56 in that area. Standard scientific calculator is going to be your friend. Figure out where that log button is and how to push it. Okay. There's plenty more examples. Sure. You're very welcome. There's plenty of other examples. Do you want to see one more of any of these other crazy ones? Is there anyone here that you're like, yikes? 13? 13 is a yikes? Oh, 13 does look like a big yikes. Okay, looking at number 13. I see, here's my variable in the exponent, and it's sitting on this base. So that's the thing I need to isolate and get by itself. It's having a multiplication by 6, and it's having a subtract by 2. So I'm going to handle the subtraction first because reverse PEMDAS tells me that I need to undo addition subtractions before I can undo multiplications. And then I can divide by 6. Four divided by 6 is 14. And now I'm back to, let's put it in logarithmic form. This is the base. This is the exponent. This is the result. Remember, you trade it out this way. Base exponent equals results can be traded out for log of the base of the result equals the exponent. What? It's not that funny.
Kevin just smelled something. Kyle.
The math is really getting to them now.
It is. Oh my God. Logaroonie Tunes. Are you okay? I thought you were going to be locked in. Alejandro, you're letting me down.
What? What am I doing?
You came in to keep them locked in.
I'm in charge of her.
In charge of her. You don't take responsibility for everyone else at the table.
I'm sorry. I'll step in my game.
Okay.
Guys, get to work. Now.
Who's this midget telling me what to do?
All right. Did what I did make sense?
No, can you please elaborate?
You were busy giggling.
No, that was them.
Okay, reread what I wrote. Before you say it doesn't make sense, reread what I wrote. Questions on what I wrote? There you go. It's just like in English class. Miss, what do? I don't know. Did you read the directions?
Yeah, Caitlin.
Wow.
Aren't you the one that's looking for answers?
All right. I'll leave you guys to finish solving that one. Let's close up today by talking about the natural log. The natural log is an irrational number. Hi. The natural log is the logarithm of some base that is not a whole number. We call this base E. I don't know why it's E, but Caitlin E. This is what has been going through my brain since you had me start calling you Caitlin E. It's Euler's number. Okay, thank you. My math historian in the room telling me where it's coming from. So E stands for Euler's number. I know it sounds like I'm saying oil, but his name is like German or something, and it's spelled E-U-L-E something. But it's pronounced Euler. I don't know, not English words. And it's about 2.71 something. It occurs very, very often as the base of either exponential or logarithm functions that describe real world scenarios. The spread of COVID, uncontrolled and unchecked, was an exponential growth function. Okay? And its base was E. Earthquakes, the Richter scale is on base 10. I think when like populations start reaching the threshold of how many organisms can subsist off of this set amount of stuff, of resources. Oh, hi, environmental sciences. It's good to see you. Did not realize you're going to pop up in my Algebra 2 class today. You're going to quickly find out how little I know about environmental sciences. Please call me out. But when you have a limited amount of resources and this population, yes, at the start, it seems to grow exponentially, but at some point, there start not to be enough resources to sustain that growth, and the graph starts leveling off and starts looking logarithmic. Okay. Natural exponential functions with base E are called natural exponential functions, and it looks like this. E to the x. Y'all know where that's from, don't you? Oh my God, do it nice and loud. Okay, I'll take it. Sure, I'll give you 1 extra points for the lameness. If you'd memorized it and you'd done it loud enough to trigger my microphone over here, would have given you like 10 points. You want to try it again? Want to get the whole class involved? Yeah, go ahead. You want to study it and do it on Thursday?
I only don't know one line. I know all the rest.
It's trig functions. Uh-huh.
Tangent.
Close. Secant, cosine, tangent, sine. Secant, cosine, tangent, sine. Okay. If you guys do it loud, like if you were at a pep rally, and my microphone's got a trigger because it heard you. No, from there. Don't cheat and come over and yell into the microphone. From there. Oh, no. All right. We're going to write each of these natural exponential equations in their logarithmic form. It's exactly the same as the other way, but instead of writing the word log, log, we're just going to write ln for natural log. So as you can see here in number 1, the person who started writing these notes for me, thank you very much, stacked a natural log right up against a exponent base E. They undo each other, leaving you with just the exponent. And if we want to go from logarithmic form to exponential form, that ln tells you, oh, we have a base E. But otherwise, the rules stay the same. The rules to condense expressions with the properties of logs stay the same because this is just a logarithm. It just has a base as a letter instead of a number. And the solving is exactly the same. Do you want to see any of these solved?
Yes.
All right.
16.
16. You meant 15. Just kidding, JK. Oh my goodness, yeah. I'm trying to get to the end of the year, guys. Okay, I have this many natural logs. So I'm stuck looking at the operations between them to try to condense them, because step one to solving logarithmic equations, which this is because that's a natural log, is to get it to be one log either by itself completely or one log on each side of the equal sign. So the left side, that's a quotient property. So I'm going to rewrite that as the natural log of 72 divided by 4. And on the right-hand side, that's a product property. So that's going to be the natural log of those two things being multiplied together. And again, just using the square brackets to help you see that it's all of that I'm taking the logarithm of. Do I have one logarithm on each side of the equal sign? Are the bases the same? Yes, because they're both natural logs. The natural logs have a base of e, and while that is a letter, it's not a variable. It's just not a whole number, us easy to memorize. Okay?
So we could say 72 over 4 and the other side.
Yep. And then that is a fairly simple equation to solve. All things considered. Yes, there's a fraction in there. But at this point in your Algebra 2 careers, I feel like you're much more capable of handling these kind of fractions than the ones we did in like Unit 9, Unit 8, when did we do the rational expressions? With all of the long division and the polynomial craziness? 7?
I know the exact.
Yeah, you're traumatized. I can see the PSD in your eyes.
PSD.
Oh, PTSD. All right, what's left? Oh, growth and decay and compound interest. Yeah. Yeah. You already have this expression. Write it down if you don't. Now, I'll be real with you. No cap.
Okay.
I'm really bad at these. I am so bad that I'm going to end the stream here.
We're cooked yet.
Because I'm cooked and overdone. Goodbye.